Okay, welcome to Section 8.3, Describing and Analyzing Data. The objective here is to calculate numerical descriptors, such as the measures of central tendencies, standard deviation, and percentiles. Displaying data in a clear and informative way is an important and necessary step in research, just as important as describing data numerically so that they can be compared and analyzed. Our first topic is the arithmetic mean. The mean is the sum of all data values divided by the population, the number of data points. Formally, the formula for population mean is given to us here. And notice we're using mu to denote the average. This is the sum of all data points. And this is the number of data points. So they're using the subscript x sub I. So x sub I is x1, x2, x3, all the way up to xn, where I is the ith data value and n is the number of values in the population. And again, I'm just re-emphasizing that mu is the population mean, or the average of the entire population. We see that the arithmetic mean has another way to be represented, and this is when we're talking about sample data. That means the data does not represent the entire population, and we call this x bar. So x bar is equal to the sum of all data points divided by the number of data points. So we see that really it is exactly the same thing. They're both the population mean and the sample mean are taking the number of data points you have, adding them up, and dividing by the number of data points. But a sample mean can and often will differ from the population mean because it's made up of less data points than the population. So sample mean often differs from population mean. A sample of the number of sick days students in Professor Hudak's Nature of Mathematics class took last year is listed below. Calculate the mean of the sample data. So we want to add up all of these numbers. And we get the sum is 54. And then we count the number of terms, 1, 2, 3, 4, 5, 6, 7, 8. We divide that by 8. And 54 divided by 8 gives us a mean of 6.75. The median of a data set is the middle value in an ordered array of the data. So in this example, it says that the VO2, which is the volume of oxygen max score, is the amount of oxygen that a person's body can transport and use during exercise. It is measured in liters of oxygen per minute. Given the following VO2 max scores for 12 women, find the median score. And the first thing we have to notice is the list is not sorted. So the first thing we want to do is rearrange the list so that it is sorted. And now the median is the middle value. So we can count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces of data. So 1, 2, 3, 4, 5, 6. This is the middle. We have 6 pieces of data to the left and 6 pieces of data to the right. So we need to take the average of 27.0 and 27.1, and that will tell us the median is 27.1. 0.05. Okay, so the next topic is mode. The mode is the value in a data set that occurs most frequently. Here in this set, if we look through it, we can see that the number 12 shows up more than any other, and we would say that 12 is the mode. In example 3, we're asked to find the mode in each of the following data sets. Example A is talking about favorite color among students. And if we go through the list and count how many times each data point shows up, so red shows up 4 times, blue shows up 1, 2, 3, 4 times, pink shows up 2 times, violet is once, purple is once, green is 2 times, and white is once. We see that this example has 2 modes, and it says to state whether it is unimodal, bimodal, multimodal, or has no mode. We see that this is a bimodal example. We have 2 pieces of data that show up an equal number of times, that is more than any other. Example B, car make in a company's parking lot. So if you were looking at the other employees and what they drive in the parking lot, and we were to count through the car makes, Honda shows up 3 times. Toyota shows up 3 times. Chevy, again 3 times. Buick is 1. Ford is 2 times. Chrysler 1, Lincoln 1, Dodge 1. So because we have more than 2 modes, anything more than 2 we call multimodal. And if we go back to our previous example, this was unimodal. And if all of the data shows up an equal number of times, then it has no mode, or it's non-modal. Example 4, find the mean, median, and mode of the following data set. And after we find the mean, median, mode, we're asked to decide which measure of the center we think best describes the data set. So because we're being asked to find the median, we need the set sorted. So I have it sorted on the next slide. And let's start with our mean. Oh, I gotta reset my calculator. There we go. So we see the sum of our data was 410. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces of data. So the mean is 410 divided by 11. 37.27. Because we have 11 pieces of data, 1, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5 to the right, which makes this the center value. So we can say the median is 26. And our mode is the piece of data that shows up the most. The mode is 15. So if we look at this, the mode is not a good measure of the center because we only have 2 data points below the mode. We have 7 data points above the mode, so we would say this is not a good measure of the center. The median has an equal number of points above and below, and so does the mean. If we were to plot the mean, it would be in here. It would have 1 more point below than above. So now the other things to look at is what's the difference in the range. So 26 is 15 away from the minimum. So it is the minimum plus 15. 26 is 84 minus 26 is 58 from the maximum. So it's the max minus 58. So that doesn't look too such like it's a good balance. Let's check out the mean. 37.27 minus 11 places the mean at 26 above the minimum. And it is going to be the maximum minus which is 57 from the maximum. So both the mean and the median look like they are equally set to be a measure of central tendency. Neither of them gives a better benefit over the other. Both of them are placed in the middle of the set. The mode would not be a good measure of the center of the data. Sometimes when we're collecting data, we get numbers that are extreme compared to the rest of the data. We call these numbers outliers. And a way that we can identify an outlier is that its value is more than 4 standard deviations away from the mean. Now, we haven't done standard deviations yet, but we will. And then this becomes a tool that we can use to help us identify outliers. Range of a data set is the maximum value, subtract the minimum value. So if we were to find the range for this data set, we want to find the minimum and the maximum. Looks like the minimum is 5. And the maximum is 54. And if we subtract 54 minus 5, we get 49, and that's our range. Standard deviation is a measure of how much we might expect a member of the data set to differ from the mean. The formula for finding the population standard deviation, and again, I'm emphasizing that now we're focusing on population and not sample, is this is little sigma, and inside we have big sigma. So little sigma, and the summation is big sigma. Big sigma is used to denote that we're adding up a list of numbers, and little sigma is used to denote the standard deviation in the data set. So here our formula is sigma is equal to the sum of the xi is the data value minus the population mean in parentheses squared, and the sum means we have to do this for all data values. So x1, x2, x3, all of those. And then n is the number of data points or the size of the population. Again, I'm putting a note at the bottom to say that little sigma is the population standard deviation. And then next is the standard deviation for the sample. So again, the formula is very much the same. The only thing that you're going to see here that is different is that S is used, or sometimes SD, if we're talking about sample population. So the standard deviation is S or SD when our focus is on a sample. And all of this is the same. We're taking the sum of each data point minus the mean, but again, notice that this is the mean of the sample, not the population mean. And then the final difference is we're going to divide it by one less than the population size, or I should say the sample size. So here we're going to calculate the standard deviation. It says, calculate the standard deviation for a sample, there's the key word, of 9 ages of students working with a university theater production of Macbeth. Because it's a sample, we want to use this formula. So we start by writing our formula. And if we count the data points, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have n is equal to 9. And we can calculate the average. I've done that down here already just to save us some work. And that x bar is going to go into our formula right over here. So that's where the 20.67 needs to go. So just to recall, n is equal to 9, x bar is equal to 20.67. And here we can calculate each of these. So now xi is the first x value. So this is x1 is equal to 17. So it means we have 17 minus 20.67. minus 20.67, and we get negative 3.67, and that's what will be in the parentheses, and we will square that, and that gives us 13.46. We'll round it to 13.47. And then we'll do the same thing here. X2 is equal to 21. 21 minus 20.67 will give us 0.33. And then we will square that and get 0.11. So we're just rounding to the hundredths to make it easier to handle. This is our third data point, 18 minus 20.67. Negative, I'm going to go back, negative 2.67. We want to square that. We get 7.13. So this will be the same. 18 is x4 and x3. x5 is 24. 24 minus 20.67, and we get 3.33, and when we square it, 11.09. "21" we had done already. It was the second row, 0.11. And now 20 minus 20.67. And we square it, 0.45. And 28 minus 20.67. And when we square it, 53.73. And now we want to add all of these numbers up. And that gives us a sum of 96.01. And we see that is the sum of each x value minus the mean in parentheses squared. So each term squared, and then we sum each of these terms. And that's what the sigma is telling us to do. That means now we have the numerator of our standard deviation. So we can write that the standard deviation is the square root of 96.01. We have x1, 2, 3, 4, 5, 6, x7, x8, x9. So n is equal to 9, but we want n minus 1, so we're going to divide by 8. All of this is underneath the square root, so we can go back and say 96.01 divided by 8, and then we can say find the square root of this number, and we get 3.46. So that is working out the standard deviation by hand. This was with a sample population. If we had the entire population, we would use the other formula. It's very similar. We just would have had a mu here, and we would have used n instead of n minus 1 in the denominator. But when we get to larger files, we don't want to do this by hand. We want to do this using a calculator, or even better, a spreadsheet. So we're going to enter, instead of into a calculator, we're going to enter the following data into a spreadsheet. And I've set up a Microsoft Excel sheet with all of this information already available. And if I click on this link, there we go. So you can see that we have all of the data from the slideshow right here in the spreadsheet. And if we want to find the sample population, because it is the entire senior class of Richmond High School, that means it is the entire population, we would want to use the standard deviation of the population, and that's what I have typed into this cell down here. So standard deviation of the entire population has a formula. So in Microsoft Excel, you would simply type in all of your data, and now whenever you want Excel to use a formula, you have to start with an equal sign, equal. Now, once you do that, you're telling Excel, I'm giving you a formula. ST for standard, DEV for deviation, and notice the list has two different ones. It has .p and .s. .p is going to be for population. That's what we want, parentheses. Notice that it gives us instructions. First, it wants the numbers. So number 1, 2, 3, 4, I'm just highlighting them all. So that's all of the numbers that I want Excel to use. Close the parentheses and hit enter, and we get a standard deviation of 72.84. Now, we can do this again for here's Twitter tweets. This is a sample of 24 students. And with the sample of 24 students, we would want to use the sample standard deviation. And the answer is here already. But if we look up at the formula bar, it says stdev.s. So we can do this again and show how to get the answer. Start with an equal sign because you're telling Excel you want it to use a formula. STDEV is standard deviation. .s is for a sample population. Parentheses to start entering your data. Click on the first number and drag and highlight all of the numbers you want Excel to use. Close the parentheses and hit enter. And the standard deviation of a sample is 10.33. And this is much easier than doing it by hand. So tools like Microsoft Excel become really valuable with research and data collection and analyzing the data. Let's go back to our presentation. So we got our standard deviation for the SATs. Let's just go back and grab that number. It was 72.84. All right, and we can move to our next slide. So the next topic is the empirical rule, and it states that when the distribution of a set of data is approximately bell-shaped, we can estimate the percentage of data values that fall within a few standard deviations of the mean in the following way. So notice that the mean, denoted with the mu, is right in the middle. It goes to the height of the bell curve. And this is one standard deviation to the right of the mean, one standard deviation to the left of the mean, and it is 68.27% of the data, but we say it's approximately 68% of all data points. If we continue to use the empirical rule, we got our 68% here, but now we have 95%, and we can say that 95% lies within two standard deviations of the mean. So here we see 2 standard deviations to the right, 2 standard deviations to the left, and that gives us 95% of the data. And then the empirical rule continues with 99.7% of the data lies within 3 standard deviations of the mean. Again, from the mean, we go 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left. And in this image, each sector of the bell curve is calculated. So we see that just this sector of the bell curve, meaning just the portion 1 standard deviation to the right of the mean, is 34% of the data. Just the portion that lies between 1 and 2 standard deviations to the right of the mean is 13.5% of the data. So we can break all of this down and find each of the sectors of the normal curve, and that will help us calculate percentages as well. So example 7, using the empirical rule, suppose you suspect that emergency room waiting times for a local hospital have a bell-shaped distribution. The data have a reported mean, so this is our mu, of 116.9 minutes, and a standard deviation, this is our sigma, of 56.1 minutes. Part A says identify the range of waiting times that are 95% of patients are likely to experience. Well, at the mean is 116.9 minutes, and we see that 95% goes to standard deviations in each way. So 116.9 minus 2 times 56.1 will equal the left side or the lower number, and 116.9 plus 2 times 56.1 will equal the right side of our range, One 16.9 minus 2 times 56.1 gives us 4.7 minutes. One 16.9 plus 2 times 56.1 gives us 229.1 minutes. So 95% of patients will wait between 4.7 minutes to 229.1 minutes. And that is the answer to part A. Part B says estimate the percentage of patients that will wait less than 2 hours and 53 minutes. I'm going to clear this work out so I can work on part B. So, first thing we need to do is convert this to minutes. 2 hours is equal to 120 minutes plus the 53 minutes we have here is 173 minutes. We want to know how far is 173 minutes away from the mean. So let's subtract 116.9 and we get 56.1, which happens to be our standard deviation. Because it is greater than 116, it must be to the right. So it lands exactly on this bar. The question says estimate the percentage of patients that will wait less than this. So that means all of this part of the curve, we want to know what percentage this represents, because that's less than. So to calculate this, we say that we know that this is 34% of the data, and everything from the mean to the left is 50%. So 50% plus 34% means that 84% of the patients will wait 2 hours and 53 minutes or less. So percentiles divide the data into 100 equal parts and tell you approximately what percentage of all data lies at or below the given value. So lies at or below, and that's the important part of the interpretation. we see that we have a sample multiple choice problem displayed here. It states Sierra received her scores from taking a mathematics placement test for her chosen university. Choose the best explanation for what it means for her to be in the 61st percentile. A, she correctly answered 61% of the answers on the test. No, that's just her grade, if that were the case. We're saying, what does it mean for her to be in the 61st percentile? If we go back to the definition, lies at or below. Choice B, 61% of the people taking the test scored the same. No, that's at, that's not below. C, Sierra's score was at least, and there we have at least, that implies an inequality. Sierra's score was at least as good as 61% of the people taking the test. That looks right. And D, Sierra missed 39% of the test questions. Well, that's the same thing as question or as answer A. Instead of saying 61% were correct, 39% were wrong. So those two were the same, just worded differently. The answer choice here is C. The next topic is called quartiles. Q1 stands for the first quartile, and that means that 25% of the data is less than or equal to that value. Q2 is the second quartile, and that means that 50% of the data is less than or equal to that. We have a note down here that S2 is the same as the median. These are equivalent. Q3, the third quartile, means that 75% of the data is less than or equal to this value. So we're asked to find the quartiles for the following data. To do this, we always start with the median. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces of data. So that means 2, 3, 4, 5, 6. There's the middle, 6 to the left, 6 to the right. That means that our Q2, which is the same as our median, is the average of these two middle values. So it's 11.5. That's our Q2. Now to find Q1, you find the median of the left half. So to find the median here, you would take the average of the two middle values. So Q1 is 7. And then Q3 would be the median of the right half. Q3 would be 12.5. So we have Q1 is 7. Q2 is 11.5. And Q3 is 12.5. That means 25% of the data is less than or equal to 7. 50% of the data is less than or equal to 11.5. And 75% of the data is less than or equal to 12.5. Finally, example 8 is descriptive statistics. In this example, it says to receive federal financial aid for higher education, students must first complete a free application for federal student aid form, commonly called FAFSA. And it says the given data gathered from FAFSA on the number of applications by state. We're going to use Microsoft Excel to find the minimum, the maximum data values, the mean, the median, the mode, the range, and the standard deviation for the data. So before I open this file, Microsoft Excel has a function called quartile. So we always start Excel with an equal sign. We'll use quartile, percent, and then we'll choose the data. And then we put a number here. If we put the number 0, this will be equal to the minimum. If we put the number 1, that'll be equal to Q1. The number 2 would be Q2. The number 3 would be quartile 3. And the number 4 would be the maximum. So we're going to use that quartile function in Microsoft Excel to accomplish finding these descriptive statistics. Let's open up the Excel spreadsheet. So here you see is all of the FAFSA data by state. And if we go through this list, you can find the max, the min, you can find the quartile range, um, the mean, all of these things would be able to be calculated. So I found a 0 here, so that's going to be our minimum. And then someplace in here is our maximum. So we see that 0 is the minimum. Up here in the formula bar, you see quartile, the data, and 0 to find minimum. We're going to do that now. Remember, I'm going to start with an equal sign, and after the equal sign, we're going to use quartile. That is the Microsoft Excel function, parenthesis. Notice the first thing it says is the array. Since I have all of the data in one column, I'm just going to click on the B column. That's the array of data, comma. Now it says, which quartile do you want? Since it's the minimum, I put a note here that's quartile 0. Close the parenthesis, hit enter. Now for the maximum value, we're going to do quartile 4. Okay, and it's going to be equal to quartile, parenthesis, click on the column with all of our data, comma, quartile 4 is the maximum in the data, and we get 197,594. The range is equal to the maximum minus the minimum, and we see that the range is equal to the maximum value in this case. Quartile 1 equals quartile, parenthesis, the column with our data, comma 1, close the parenthesis, and that means that 25% of our states had less than or equal to 380 FAFSA applications. Quartile 2 equals quartile, parenthesis, choose our data, comma, number 2. This is the same as our median. The median is 9,747. This means that 50% of our states had 9,747 applications for FAFSA or less. Let's do quartile 3. We get 27,845.5. And interquartile range is Q3 minus Q1. This is used if you're developing box and whisker plots. We can use Microsoft Excel to calculate the average for us. Average, oh, forgot my equal sign. You always have to start a formula with an equal sign. Click on the column. The average value is 21,611. The median. So Microsoft Excel has a median function, and this should give us the same answer as Q2, 9,747. It matches the 9,747. And now we can go to mode. And what if we have multiple modes? So we can do .mult for multi-mode. And we have 3. So 3 is our mode. All right, so there is our descriptive statistics. And we did this using Microsoft Excel. The majority of this work was done using the quartile function. All you have to do is, put your data into Excel. I like to use columns. It gives me an easy way to select all of the data. Excel ignores the text. It only focuses on the numeric values when using functions like average and quartile and median. Let's go back to our presentation, and that's the last slide. That's where we end this presentation. So watch the video, pause it, take notes, and then complete the assignments, and send me questions if you have them.